Good evening, and thank you so much for joining us for our next ISA webinar on photovoltaic basics. We are very fortunate to be joined by two fantastic presenters, Antoine Duzier and Fred Sugar from the French National Institute of Solar Energy and the East African Centre for Renewable Energy and Energy Efficiency, respectively. This is the third webinar that ISA has put on as part of our STAR-C project, designed to support our members and other stakeholders at this challenging time. There will be many more to come, so please stay tuned and keep in touch. We'll be announcing more in the coming weeks. We will be making a recording available on our ISA Infopedia page, and I'll be putting a link up to that at the end of this webinar. If you haven't already looked at it, it's a fantastic resource on solar, a one-stop shop for all things solar, and we hope that you continue to use it. I do know we'll be running a Q&A session following the presentation. Please send in your questions, and our fabulous presenters will try and respond to as many as possible during the final part of this webinar. Once again, I'd really like to thank, on behalf of the International Solar Alliance, our two fantastic presenters, Antoine and Fred, and the French National Institute of Solar Energy and Energy Efficiency, and the East African Centre for Renewable Energy and Energy Efficiency for their support in putting on these webinars. We're really most grateful, and I know that today is going to be a fantastic and fabulous presentation and of great interest. So without further ado, I'll now hand over to Antoine for the first part of the presentation.
Yeah, thank you, Fiona, for the presentation. And we at INES are very pleased to be part of this webinar. As you have probably seen by attending this webinar, we will focus today on solar PV basics. That is to say, how to characterize solar resource. And second part, what are the main system components when we are talking about a PV system. So I will manage to present the first part about solar resource, and my colleague Fred will manage the second part about PV components. So the main objective today is to give you a large overview of how system work and what are the main technical values that you can use for your own PV projects. So we hope that you will gain a nice knowledge to undertake your own project after this webinar. If we look at the main agenda of the first part and then the second part, we will first focus on basic terminology. What are the main technical terms when we are talking about solar resource? And also, what are the common values that we use for PV projects, especially for projects in Africa? How do we characterize solar potential for a specific site? And then after defining what is PV effect, how PV module work, Fred will work with you on what are the main components in terms of modules, how do they perform under specific meteorological conditions, but also what are the other components that you need to take into account, which are charge controllers, inverters, which types you can use, how do they perform, and lastly, one of the major components in the off-grid PV system, which is batteries, how to maintain it, how to design, and also what are the characteristics of such components, which are batteries. So first, for the part about solar resource, which is always the first part you need to consider. A nice thing to have in mind is what is the origin of this solar potential that we have on Earth. Basically, solar energy, of course, is generating by the sun and from sun-specific reaction, which are called solar fusion. So basically, on sun surfaces, you have fusion reaction between hydrogen 2 and hydrogen 3, which are tritium and deuterium. And when you do a fusion reaction with these two components, you will create a large amount of energy in space. And so solar energy is basically generated by heat and pressure by this specific nuclear fusion. Next step is as far as you are from sun, you will get more or less energy. So planet Earth is located approximately 150 million kilometers from sun. So we will receive a specific amount of power and energy at Earth's surfaces. So a good thing to remember is two specific values. One specific value is what is the power per square meters that you can receive at atmosphere level, so before crossing the atmosphere barrier. And this value is given on the schematics you can have a look on. And this value is called solar constant, and the value is 1,360 watt per square meters. So this is the amount of power that you can receive on 1 square meter, on each square meter on Earth's surfaces. Once this radiation, this energy cross the atmosphere, you will have some losses due to mainly diffusion in some atmosphere particles. So at Earth ground, you will approximately receive 1,000 watts per square meters if you are in clear sky condition. So that is a very, very important values to have in mind, that on each square meter on Earth at ground level, you can receive about 1,000 watt per square meters of power from the sun. So this will help us to understand how much energy that we can have, for example, in 1 hour, in 1 day, in 1 month, during 1 year. So if we take all the potential of solar energy, that is to say, we have just seen that we can receive 1,000 watt per square meters for each square meters at ground level. So if you take all the square meters from half of Earth, that is day, and the other half is night, if we take this half Earth, you will get a fantastic amount of energy during 1 year that you can then convert into electricity. So this schematics that you have on the slide represent the solar potential that you have on Earth, which accounts for about 23,000 terawatt of power that you can actually convert into electricity. And what is very interesting is to compare this potential with other energy potential. So we can compare to other renewable energy potential, such as wind, hydro, waves, or also biomass. And what we see directly from this graph is that the potential of solar energy is far more interesting, and the amount of energy that you can get from solar energy is far more important than other renewable energy. The second point is that compared to fossil fuel, which are called gas, oil, and coal, basically. Also, you can compare the potential per year of solar energy with the reserves of these fossil fuels. And what you can see is that we have much more potential per year than the potential of these fossil fuels for many, many years in the next future. So that's an interesting view of global energy market, to know that solar potential will come every year with regards to fossil fuel reserves that are decreasing dramatically. So we know that the potential on Earth is dramatic, and we have a lot of energy to be converted. A point is that this energy is, of course, intermittent, because you have day and night during the year, and you have also in some specific regions seasons. You might know that seasons on Earth are due to one specific angle, which is called a declination. That is to say that the circle on which Earth is rotating around Sun, if you take the rotation axis of the Earth, is not perfectly perpendicular, but it's a little less than perpendicular, about 23 degrees. So if you see, if you have a look on the schematics, if you take the right of the schemes, December solstice, for instance, you see that if you are located in the northern hemisphere, you are closer than the Sun compared to the southern hemisphere. So it's actually winter for you. And that's the other way around, 6 months later. If you are locating in the south of Earth, you are closer than the northern hemisphere. So it will be winter for you in the south. So intermittency of solar energy is due to the rotation of Earth around itself, but also on the rotation of Earth around the Sun. And this can be characterized by what we call path of the Sun. And the path of the Sun, if we are locating on Earth, we are not seeing the Earth moving around the Sun, but we are looking for the Sun moving around our head. And this path of the Sun above our head is only depending on the latitude of the site. If you are very close to 0 degree latitude, which means near the equator, you will find the path of the Sun approximately like Nairobi in Kenya. This is the picture at the center of the slide. You see that the path of the Sun is is often above your head. That is to say that the Sun is very high in the sky. So you will get a lot of energy. And also the time of the day will be quite constant during the year. If you take two other latitudes, North Hemisphere or South Hemisphere, such as Casablanca in Morocco or Cape Town in South Africa, you see that the path of the Sun is not completely above your head, but the elevation angle of the Sun is quite low compared to Nairobi in Kenya. And this path of the Sun, we can characterize it by simply two angles. The first angle is azimuth angles. Azimuth angles represent the angle on the horizontal surface that you have between your system, for example, your PV system, and the Sun at a certain moment. Second angle is a solar elevation angle, and this is just the angles between the height of the Sun, so the elevation of the Sun, compared to the horizontal axis. So with these two simple angles, you can characterize where to find the Sun at a certain moment of the day all year long. So this will be of crucial importance for your PV system. Because depending on your region, you will get more or less energy. This was for characterize path of the Sun in terms of intermittency, and we will next see what are the values that you can get in terms of solar potential in 1 day, 1 month, or 1 year. But before to give these values, we need to define technical terms that we use in solar energy. First term is what we call solar irradiance. Solar irradiance is the rate at which the sun's energy strikes an area at any given moment. So it's a power value, and it is expressed in watt per square meters, or of course kilowatt per square meters. So we have just seen one value of irradiance, which is 1000 watt per square meters in clear sky conditions. So you can remember that solar irradiance is power. Second term is solar irradiation. And solar irradiation is actually the accumulated amount of sun's energy that also strikes an area over a period of time. So you are basically accounting for many solar irradiance, and you sum the different value of solar irradiance to get energy. And this solar energy is called, in solar technical terms, solar irradiation. And of course, as it is an energy, it is now expressed in watt-hour per square meters or kilowatt-hour per square meters. Last term, and it's a term that is very often used for off-grid system, is what we call peak sun hours. And peak sun hours are actually the number of hours at a given irradiance. So for instance, if we take solar irradiance of 1 kilowatt per square meters, we can say that if we have a solar energy of 2 kilowatt hour per square meters, it means that we have 2 peak sun hours, and each hours at a given kilowatt per square meters. So these are the three terms you might remember: power, which is solar irradiance; energy, which is solar irradiation; and number of hours at a certain power, which is peak sun hours. And these three terms are very often found in solar database, for instance. So it will be very useful for you to remember this term. Next, some other terms that you might use in your project also. The components of the global energy that you can have on Earth are actually from different sources. You have basically two main terms of solar energy: the beam energy, which comes directly from the sun, and the diffuse energy, which is the direct energy that is diffused by mainly the clouds at atmosphere level. So if you want to account for all the energy you can get on a specific site, you have to take one, the beam energy, and second, the diffuse energy at a horizontal plane. If you use a tilt plane, which is often the case for solar energy, you will have to add a third term, which is reflected energy. You know that some energy can be reflected at ground surface, depending on basically the brightness of the surface. So if you have snow, which is very bright, you will have a lot of reflected energy. Whereas if you take, for instance, water, which is quite dark, you will get a very low reflected energy. So please remember that if you consider all the energy of your projects that come from the sun, it can come from beam components, diffuse components, and lastly, reflected components. Now, if we look at the values for both irradiance first and then irradiation secondly. Irradiance, I've just given to you the clear sky values for irradiance, which is 1000 watt per square meters for clear sky condition. It means a sky with no clouds, so a perfectly nice weather with only sun, so only a direct power from the sun. If you add some clouds in your sky, so if you have a cloudy day, for instance, you will get less power, of course, from sun. So you will go from 1000 in clear sky condition to 1,000, 2,000 maybe watt per square meters if you have a lot of clouds in your sky. And for very bad weather conditions, when you have a very dark sky, this irradiance value will even go lower, 10 watt per square meters, 20 up to 30 watt per square meters if you have a very dark sky, for instance, in storm conditions. So please remember these values of irradiance from basically 0 up to 1,000 watt per square meters in clear sky conditions. This was for power, and now let's have a look on energy, which is irradiation, solar irradiation. This is a nice irradiation map that you can find easily online. This map is actually giving you what is the amount of energy that you can collect on the annual level or on the daily level for each part of the world. So you see all the continents: America, Africa, Europe, Asia, Australia, and you have colors that will give you the amount of energy that you can collect. Basically, if you are in purple or red color, it means that you receive a lot of energy each day and each year on your specific site. So you can see here very simply that the main region, the regions where you can have a lot of solar potential are basically South America, West America, of course Northern Africa and Southern Africa, Middle East, and the north of Australia as well. So here are the main regions that are very nice for solar energy. So they are of course very nice for solar photovoltaics as well. In terms of values, you can see that on Earth you can receive from about 700, 800 kilowatt hour per square meters in very poor potential regions, such as north of Europe, for instance. And you can go up to almost 3,000 kilowatt hour per square meters in the regions when you have a lot of potentials, such as Sahara or Salar Uyuni in Chile. So also, these are also nice value to have always in mind concerning your country, to have this value to make your own projects. Of course, if you have 2,000 kilowatt hour per square meters of solar potential, this will give you a constraint in terms of after design, because you will not be able to convert, of course, more than this solar energy. Let's take, we can take now two more specific examples. First example is Kenya. Here you have the zoom on Kenya country with the same color scale at the below the map. So you see that in Kenya you can go up from 1,400 kilowatt hour per square meters in the region where you have less energy in Kenya, for instance, north of Nairobi. But you can also go up to twice this energy, that is to say more than 2,600 kilowatt hour per square meters. For instance, near the border of South Sudan or near the border of Ethiopia. So you see that in one country, you can have a region that with twice the potential of energy compared to other regions. So it's very important to choose well your site for your solar projects. Second example is Botswana, also in Africa. Here you have also the same map, but you can see that in Botswana, the solar potential is much more homogeneous over the country. You remember in Kenya, we were from 1,400 kilowatt hour per square meters up to 2,600. And here in Botswana, you go from 2,000 up to 2,600. So it's a country with a much more potential on a global point of view. How to find this data or this map? You can find on different database. Here you can find a list on the most common database used in the solar PV market. The first one is NREL. This is basically for the American continent, and it is very nice data set. You have also PVGIS, which is a database designed by the European Commission. And this database is covering mostly Europe and all the African continent as well. And then you have also two other nice databases, which are SODA and Solar GIS, which you need to pay for receiving a database for about $200 to $300 for one specific site. NREL and PVGIS are databases that are available for free, so it is very nice to use this this type of database. And to finish with solar resource, we have just analyzed solar potential for different regions, but we know that we can also have a positive impact on the solar resource that we can get on one specific site by just changing some geometric properties on our solar system. And the two main geometric properties that we can change are tilt angle of your system and, of course, azimuth angles of your system. Maybe we can start with azimuth angles, which is, I think, the most easy angles to undertake. If you are on the north hemisphere, you will need to face the sun over the day, so you will need to have an azimuth angle facing south, of course. And it's the other way around if you are managing a project in south hemisphere, for instance in Cape Town, South Africa. For this site, of course, you need to face sun, so you need to have an azimuth angle facing north this time. This was for azimuth angles. And of course, tilt angle is also very important, because as you change tilt angle, you will face more or less the sun, so you will be able to collect more or less energy. Of course, the best tilt angle you can choose is only depending on the latitude of your site. If you are on a high latitude, you need to have a very important tilt angle because the path of the sun is very low in the sky. And on the other way around, if you are close to the equator, the sun is very high above your head, so you need to have very low tilt angle to face the sun, very close to the horizontal axis. To illustrate this idea, I just put this nice map, and this map is giving you which are the best tilt angle for each specific latitude on Earth. That you see, if you are on equator level, for instance, in Nairobi, Kenya, you will need to choose very low tilt angles between 0 degrees and 13 degrees. Whereas if you are in Europe, for instance, in France, here you can find that the best tilt angles are around 40 degrees. So azimuth angles and tilt angles are have very positive impact of your projects. Now, before going to all the system components, with all this solar resource, how can we convert this solar resource into electricity? And that's the basic of physical property of PV effects. Actually, if you take the most common PV modules that you can get on the market, which are silicon-based modules, these modules are made with two types of semiconductors. Semiconductors are materials with where you can give them energy and they will be able to exchange electrons between each other. So you can create electric current and produce electricity. So silicon cells are made with two different types of semiconductors, what we call N-type. N-type accounts for negative types. It means negative charge in this part of the cells. And P-type, which means positive types. So you have you have positive charge in these types of semiconductors. So if you put these two types all together, N-types and P-types, you have, of course, electric difference between N-type and P-types. So you have negative charge close to positive charge. And this is the definition in electricity of a voltage. So by creating these two layers, P-type and N-type, you are creating a voltage. And with this voltage, as energy is coming on your PV type, you will be able to create direct current, because the electron from N-type will have to go to P-type to close the holes, the positive charge of your PV cells. So this is how you can create electricity from two different types of semiconductors. And you can also add some front metal contacts to improve the conductivity of your materials. And silicon PV cells are also made with some anti-reflective coating to maximize the amount of energy that you can absorb and try to minimize the reflected energy that will come onto your modules. And from all solar resource, you can actually not convert everything. That will be a magical system, but you can only convert one tiny fraction of all the solar spectrum. And this amount of energy that you can convert actually accounts for about 15% up to 20% for the best technologies. So this conversion is called efficiency. And how to calculate efficiency and what is the definition of efficiency will be the start for the second part. And this part will be managed by my colleague, Fred. So Fred, I think you can now take the lead, and thank you everybody for your attention.
Yes, thank you, Anton. I think I can share from my screen, if you allow. Is that okay? Yeah, hope you are able to see my screen. Yeah?
Almost.
Yeah, it takes a bit of time to load.
Yeah, it's good for me, Fred.
So are you all there? Yeah, great. Thank you. So it's really good that you've taken us through a solar resource. We have identified potential and seen really we are able to harness this very important energy resource. So for my part, I will just have a brief overview of the component. Of course, we have quite detailed technical aspects of them. But on the essence of time, I'll cover on the brief. Of course, with the additional 2 webinars that we're going to have under this subject, then we are going to dive deeper into these components. So we all know that solar PV system is made up of small cells. Small cells that are connected, usually they are silicon cells that are connected together, and having a number of them, then we form what we commonly know as a solar PV module. So a solar PV module, as I mentioned, it has a composition or is composed of a number of parts. One is an assemblage and a connection of solar cells. As you can see from the screen, All these cells are connected in some architecture series and parallel. Then with a conductor linked to a junction box. Of course, because of the fragile nature and delicate nature of the solar cell, then it has to be protected well. So usually a solar module has a framework, mostly made of aluminum frame. Then we have on top transparent glass that really allows the penetration of solar radiation. And also at the bottom, usually we protect it, sometimes with glass and of course some insulation. So when we have this module together, at times we require to collect more energy, and that is where now connection of many modules in some architecture comes in, and that connection then we refer to it as an assemblage of many PV panels as a solar array. Yeah, so this is the basic architecture of how solar PV module is. And in general, we have three main types of solar PV modules that are commonly used for power generation. You can see from the right side of the screen, the three common ones listed. We have polycrystalline or multicrystalline silicon cells. Usually they contain many grains of crystals, and in general, when you go to the market, the prices are usually low, though this kind of panels, the efficiency are generally low than the monocrystalline, which you can see at the middle, that usually has a single continuous lattice structure. And the price of this is generally high, and the reason mostly is the process it takes for processing of these cells. So the advantage over the polycrystalline on this is that the efficiency usually is high, and later on we'll see what we mean by efficiency of a solar cell. Then we have the thin film. Thin film, this quite novel type of solar PV panels based on a very thin layer of PV materials. And the advantage of this is that they are flexible. You can carve them around something exposed exposed to the radiation, then you are able to generate. One of the challenges with it, of course, a lot of research is still underway, is that they are relatively low in efficiency compared to especially monocrystalline silicon. So usually, as I mentioned, crystalline silicon have kind of a proven record of reliability. So there are systems that have undergone continuous improvement over time, and you can bet on their reliability, especially when they come from a reliable manufacturing source. So efficiency of a unit cells is usually not a matter of concern, though it's important. As I just mentioned, that monocrystallines are more efficient than polycrystalline type and multicrystalline silicon. But now, when you look at the efficiency, what basically that means is the area of coverage. Yeah, as we'll just soon demonstrate what that means. So usually for a solar home system, a PV module of average of 12 volts on the nominal voltage usually contains, has 36 cells that are connected in series. This does not mean that we don't have panels with more cells in them. They are there, but mostly these kind of panels are used for large-scale power generation system. They are best suited for that. despite the fact that still you can be able to use them at a domestic level for solar home system. But now optimizing that kind of a panel is another issue that maybe we will be exploring during the next webinar. So as I mentioned, solar PV efficiency is important, and in general we understand that efficiency is usually the output, what is given out after receiving some input. So this is the power that is given out from the power from the sun that you expose that PV panel to. So generally PV modules are rated based on the output power. So when you go to the market, the retailer will ask you how many watts do you want? Yeah. So you'll tell them 50 watts, 100 watts, and all this. These are usually rated from the manufacturer of that PV cell or that PV module. And the rate is usually done with some specific conditions. So we provide that rate at 1,000 watts per square meters irradiance and at 25 degrees Celsius. And simply I will refer to these two conditions as a standard testing condition, because these are the standard testing conditions for solar PV modules. So when you look at the diagram, that the two figures that I've just flashed out, given that, for instance, this is just trying to justify the effect of efficiency of a cell. Given that a cell, a PV module, is exposed to 1,000 watts per square meters, or rather 1 kilowatt per square meter, and that panel is about 0.5 square meters and has an efficiency of 20%. Then generally what that means is that the input power will be the irradiance you multiply by the dimension, by the area of that panel, which gives irradiance, as you can see here, as the input power as 500 watts. Now with the efficiency of 20% of that cell, then you are able to get a power output of 100 watts from that module. On a similar case with the same irradiance, for a slightly bigger module but lower efficiency of 10%, but one square meter, we do the same. When we multiply this by the irradiance, then you got the input power as 1,000 watts. And now, considering the efficiency aspect, then the output of that PV module is 100 watts. So when you look at these two, you realize that you get the same output power from modules of different dimension, one very big and then one half the size of that. So generally, space is usually a very key aspect when we are considering installation, because the bigger space you have, then you don't have to go to very efficient modules. You can go to polycrystalline or multicrystalline silicons. So when the output power is the same, of course, the module efficiency is higher for the module which has smaller area. And usually module efficiency is not a big concern unless usually the space that you have is essence. So this figure just try to bring out one of the standard graphs that we have for a solar PV module. What I'll just like to mention that unlike other generation system, usually a PV module, the output depends or varies in voltage. Unlike a generator, a genset, which will produce a constant maybe voltage output, but a PV module, the output voltage will vary depending on what voltage you're connected that module to. And just to explain further, PV module is also one of the funny type of generators, I can say, that you are able to short circuit it without damage here, and you can also be able to read some voltage when it's open circuit. So usually we have some terminologies that are used, and this curve is a curve. The blue curve you can see is a curve that has been generated after considering one type of a PV module, and I have just given an example of a module which is 100 watt, that looks at the current and the voltage and see how these two varies at different position. So for the x-axis, you can see where I'm pointing, we have what you call the open circuit voltage. This is a voltage that is available, that you can read when the two terminals of that solar PV is open, and of course subjected to standard testing condition, 1000 watts per square meters and 25 degrees Celsius, at 25 degrees Celsius. Then when you look at the other side, when you short it, that is, you connect the two terminals and you're exposing it on the same conditions, then you are able to record some current. We refer to that as short circuit current. So when you vary voltage along the x-axis, you are able to trace this curve, which is referred to as an IV curve. So within this curve, we have some dimensions, or we have these two variables that when combined, you can be able to get maximum power out of that module. And that point where you have current and voltage combined providing the maximum power is called the maximum power point of a solar PV, and it's what rates a solar PV cell. So usually that current, usually we refer to it as current at maximum power, and remember it's usually less than short circuit current. Then the voltage at which you can obtain maximum power is referred to as voltage at maximum power. You can see it here. And it's usually also less than open circuit voltage. So this graph is very, very critical, because when you connect a battery to a solar PV, for instance, a battery is about, let's say, 14 volts, and you are charging it on a solar PV panel, then the current of that to that battery from the solar PV panel will be slightly higher than the short circuit, the current maximum power. You can see. So this one gives you indication of the charging current when you connect that's battery terminals to that solar PV. So I think there's more to learn in that, but I will have to move on because of time. We have conditions that are very key in operation, in efficient operation of a solar PV. And these are the conditions that I've already mentioned, and they are conditions that are used under standard testing condition. One of the conditions is irradiance. It's quite important in performance of a solar PV system. Then the other condition is temperature. So I will just briefly go through and I will start with irradiance. Generally, irradiance has effect to three items or three variables in a solar PV performance. One of it is the current. Usually a drop in irradiance, for instance, 1000 watt, you'll see the short circuit current being very high. When we have this to around 500 watts, then there's a drastic reduction in current. Yeah. So this generally means that irradiance is very key. Yeah. So your panel needs to be exposed to very high irradiance or to good irradiance. That's why you find when it is very cloudy, then there's less of charging, and sometimes some people go on a blackout. Then the other aspect that irradiance affects is the voltage, although very dismally or to a very small extent, that lower the irradiance, then you reduce somehow the output voltage. And when this happens to this, of course, this is an IV curve, then it also affects the maximum power that you can get from that solar PV. Then the other aspect that affects, as I mentioned, is the temperature. Temperature also has effect on both the three, the current, the voltage, and therefore the power. Usually a slight increase in temperature of a solar PV module, then it means that there is some slight increase in current. So the short circuit current goes high, and therefore also the charging current that can be available for you from that module. On the voltage, there is also a slight reduction in voltage output when the temperature of a PV module increases. And what happens, it means that all the power is, and generally there's a decrease in power output of a solar PV. So generally, when temperature of a module increases, voltage reduces, and also the output current slightly increases, as we can see on that graph. So usually the rated output does on your PV panel, when you are buying it, usually we have a data sheet. Mostly it does not mean that is what is going to generate. It means that that is what has been tested at standard testing condition of 25 degrees and also at 1000 watts per square. But this is not the reality in many cases in the field. So let's move to another very important item, and this is a charge controller. Just to be brief on this, is that charge controller is a very important component. I can say not a must to be there for a small solar system, but an important component, especially to interconnect all your components. It links this PV panel, it links the loads through the inverter sometimes, and it links the battery. So what it does is it controls charging, controls, or it protects the battery from overcharging, and also protects the battery from over discharging. So I will just move on to explain a little of how a PV charge controller operates, or a charge controller operates, so that we can appreciate that fact. So as I mentioned, it manages the interaction between the energy flow for solar PV array, a battery bank, and also electrical loads, an inverter being one of the electrical loads on a solar PV system. So as I mentioned, this gadget is important to protect the battery, especially from overcharge and over discharging. And especially for overcharging, the battery, the charge controller usually either terminates the charging by disconnecting the PV panel from the battery, or limits the charging current to the battery. So by doing so, then the battery is protected. So usually the charge controller automatically senses the voltage of a battery during the overcharge protection, and when the battery voltage is below the set point voltage, there's a set point voltage usually we refer to as the float voltage, that indicates that the battery is fully charged. When it's below that, then the charge controller will continue to connect the battery and therefore charging will continue. But when this limit is reached, when the float voltage is reached, then it either limits the charging or completely disconnects the charging process. So it protects the battery in such a way. Then in terms of over discharge protection, then still the sensing process is there, but we have a low set voltage that a battery, the charge controller is set either to completely disconnect the load when the voltage is too low, or maintain it when the voltage is slightly higher, and we call this low voltage disconnect. So when the battery voltage is still above the low voltage disconnect level, then usually the loads will continue to draw power or energy from the battery, so it will be connected. But when it gets to that level or below, then there will be automatic disconnection. So you will not be able to draw power from that battery. So we have a number of kind of charge controllers. I'll just move very quickly through them. The first one, which is very common, especially for off-grid, quite cheap to buy, are the simple on or off charge control. And these type of charge controllers are available in two types. We have the shunt type and also the series type. Then we have what we call pulse width modulation charge controllers, also available in the market. When you go, you can always see clearly written PWM. Yeah. Then this one also works on pulses. Yeah. But when it is at float voltage, then it keeps on going on and off. But the pulses varies in terms of time, depending on the state of charge of the battery. Then we have the maximum power point tracking charge controllers, commonly known as MPPT charge controllers, quite innovative, that they are able to optimize the output from a solar PV panel so that you always get the maximum output from the solar PV panel. Then we have what we call diversionary charge controllers, that when your system is full, then part of the power is diverted, sometimes sent to a heatsink, then it's dispatched from a different source. We have hybrid charge controllers that also works from multiple charging sources, can be solar PV, biogas genset, and generators, then the main grid interacting within those interfaces. Then ampere hour, which also look at the charging current. So quickly, we'll also look at the inverters, which are very important component when we look at solar PV. As you all know that solar PV systems primarily generate DC current, yeah, and also batteries. When you convert, then mostly you get out DC current. So this gadget is very important that it can convert the DC current into AC current. Yeah, so an inverter. And in the market, they are available in multiple ranges, in various ranges, not just what I've indicated. So generally, under this, we have three main categories, I can say, of solar inverters. The first one is a standalone, or sometimes we call them off-grid inverters. Then we have grid-tied inverters, and we also have battery backup inverters. So looking at the first one, the standalone or off-grid inverter, usually these are installed in isolated systems, mostly solar home systems, and also vary in sizes, from very small one ranging to about 3,000 watts, so even bigger ones can be available. So inverter generally is fed DC voltage, DC current, as I mentioned, and then converts it to AC. And mostly they draw this power from the battery bank. The battery bank usually is charged by solar PV panel when you consider this type of inverters. Then we have grid-tied, can easily be connected to the grid. They have that option, and usually they fit in to the grid electricity, which generally matches in phase and frequency to what the utility has. Usually this type also do not provide backup system. And if they are generally just to control the electronic parts of the inverter. Then we have the battery backup system, usually designed to draw energy from battery. Is capable of supplying AC voltage, AC current or energy to selected loads during utility outage. And this has also been commonly used in areas where sometimes we have grid, but the grid is not stable. There's a lot of outage, so it's a kind of a backup system. Then many they manage energy between the array and the grid, while usually keeping the batteries always charged, so that whenever power is needed and the grid has been cut, then you can always have energy or power available for you. So battery charge is maintained using an onboard charger because it's an inline kind of system. So whenever the power is available, it charges as you continue using. Yeah. So usually the extra energy is exported to the grid. Just to move on to a very important component as we close is the battery. Quite important in a solar PV system, and actually one of the delicate and sometimes very expensive component. So proper usage and maintenance of this component is really important. Just to mention that a battery's main function is to store energy, and it does not generate any. So its function is only to store the energy that you've generated. It's a key component, especially in off-grid systems. Yes. And then usually the composition of battery has got some unit cells and an average nominal voltage of each unit cell is usually about 2 volts. So for a 12-volt system, usually we have 6 unit cells, and this is usually visible, especially for flooded batteries, that you have kind of 6 stops that you can open to refill distilled water when the level of the battery goes down. So what is clearly the interactive part of battery is usually electrolyte, where we usually top up this kind of fluid with distilled water whenever it goes low, and also the electrode where we connect our components. As I mentioned, this is despite also being an important component in storing, it's also a delicate and also hazardous type of component to our human health. So electrolyte in this kind of batteries, in most cases, is corrosive. So it's important always to avoid contact with these kind of fluids. And when in contact with eye, skin, or cloth, quickly wash with plenty of water so that you minimize the damage. Usually, acids never evaporates, just like when the water level or when the electrolyte level in your battery goes down, does not mean that the acid level has gone down. What you just need to do is to top up with distilled water and you continue using it. So during charging, usually we have some gases that are emitted from the 2 electrodes, oxygen and hydrogen usually. And for this reason, you require to store these battery banks in a room that is well ventilated to avoid damage, because they are sometimes flammable, and therefore also smoking is not really advisable around them. And keep, because of the corrosive nature, also try to avoid children being close to them. And just to mention that battery capacity is very key when we are also designing. And when we are buying this battery, usually it is very, very important for us to get the data sheet of the battery, so that we can be able to read and understand how best we can use that battery. Absence of a data sheet for a battery sometimes might mean that there is compromise in the quality of that battery. So it's important always to claim one while buying. So usually the data sheet also gives the rating and discharge rates, so you can be easily read. And it's important also to know that battery capacity matters the life of the battery. So capacity falling with time below 80% of its original capacity, then it means that battery is dead. You are able to use it, but it will not give you the service that you will need. So looking at it generally gives you what distance at home when your daily loads and everything requires 20 Ah of a battery, and you have a battery capacity or battery bank of 100 Ah, then it means that you will only be discharging 20% of the battery, and therefore you will only be able to exploit 20%. So the depth of discharge of that battery will be 20%. And with time, usually this capacity starts to fall. And when the cycles, charging and discharging cycle continues, then the capacity of that battery starts falling. And at 80%, it means that you have 80 Ah. If your load still maintains at 20 ampere hour, it means that with the 80% capacity, you are discharging to 25%. So the depth of discharge of that battery is deeper. It's about 25%. Yeah. So then beyond this, as I mentioned, then your battery is same as it's dead, because as you continue, as the capacity continues to fall, then the depth of discharge is very high. With clear indications that you quickly charge the battery, it gets full within no time. When you connect a few components, then your battery discharges. Something that I will quickly go through is that you never get 100% through the processes because there are conversion processes happening, usually electrical, chemical, then back to electrical. So there are losses that are involved. So battery efficiency usually is not 100%. Whatever, this is just an example. Sometimes losses can be as high as 20% during these conversion processes. Yeah, you charge your battery, there are losses during the process conversion. You discharge the process, then combined, you can have as high as 20% loss. So just to clear up is that this is one of the components that is at high risk of overuse. Yeah, because when it's giving you what you want, you can, so it has a life, you overuse it, and therefore shortening its life. So under normal operation, daily energy consumption should always be less than what you generate. Yeah, usually for a healthy system, but this sometimes does not happen as such. So there are things that usually happen. Sometimes you have decreased insolation, and therefore your solar panel, you saw that irradiance affects the output. Then you are not able to have enough energy generated during that day as what you'll use, and therefore it means that you'll draw more from a battery usually than normal. Another thing is sometimes increase use of your battery. You can generate, yes, but now based on the design, but you are using more, and therefore what now you generate is less than what you are using, based on the number of components that you have added to your system. So this kind of overuse, as I mentioned, eventually leads to less energy generated than energy that is consumed, either low generation due to low irradiance or additional appliances or load to your system. So for accidental increase in use, or just 1 or 2 days decrease in insolation, usually has no big impact. But if this continues for a long time, then the life of your battery is usually on danger. So it's something that shortens your battery life. So daily overuse is critical to the life of your battery. So when you're designing, always factor in proper loading and therefore longer life of your system. So I think with time, we will end there, and we'll appreciate to respond to any questions that might have been posted through the system. Back to you if you.
Yeah, there are actually many questions. We can select some of these questions. And maybe I have a big echo here. Do you hear me? Yeah. Okay. Yes. Maybe we can follow the selected questions and add some comments both from you, Fred, and from me. There is a nice questions concerning the impact of temperature for a specific African country meteorological conditions, and asking if there are any specific studies that have been done to select the proper technologies. Maybe you are the African expert, Fred, but I can comment one thing is that specifically for countries near the equator, generally in these regions you have a lot of diffuse energy compared to other African countries. And you have also, of course, very high temperature. And actually, there is one PV technology that is performing very well under diffuse irradiation conditions and under high temperature conditions. This technology is thin film. Is basically the second generation of PV technologies. So in thin film technology, you can find amorphous silicon. You can find also CEGIS or either other thin film technologies. And that can be a nice technology to have in mind while designing a PV system in this region. I don't know if you have any studies in mind, Fred? I think you have your microphone, which is, yeah.
Sorry, as you say, these are some of the, what you just mentioned is one of the areas of research to try and overcome that. But what has been traditionally done in a simple way during installation, as you are mostly aware that for solar home systems and small systems, mostly they are rooftops. And of course, roofs are also good accumulation of temperature. So one of the ways to try to deviate during installation is to have some clearance, the solar PV to be slightly elevated above the roof. This is one of the methods that are being used. And of course, you use natural current to provide some cooling effect during the operation or during the day. Then we have other technologies that are under research, like the PVT. Yeah, that you are able to use to have a solar PV module combined with the solar heating system. And many other approaches that are being taken, but in general, especially on design aspects, lifting your solar modules slightly above your roof when you're installing is one of the most commonly used method that really we can say it not up, but there's some slight improvement on that.
Yeah.
So I've seen a number of questions that we may. Do we have some time, Fiona, to respond to some of these questions?
We've got about 10 minutes, so there's a bit of time left, Fred.
Great. So maybe you can go first, Antoine, as I go through the questions, and then I'll also.
There is one question concerning the power of inverters that are commonly used in the large-scale solar PV projects. I would say that for utility-scale projects now, the common power for inverter are about 500 kilovolt AC. So you have basically mostly 500 kilowatt inverters at least. So it means it can undertake a large number of PV modules, and it has generally a very high efficiency as well. So as you might know, you have different types of inverters. Micro inverters, string inverters, and central inverters. Of course, for utility scales projects, you use big inverters, so mostly central inverters. And yeah, the power is mostly around 500 kilowatts. Maybe I can go for one other questions, and I will give you the talk, Fred. There is one nice question also about the maximum efficiency you can get from a solar cell. This is a good question because it depends on the technology. If you take, for instance, silicon cells, then the theoretical maximum efficiency is about 33%. So it means that under the best industrial process conditions, you will be able to convert around 1/3 of all the solar energy that you can get. This is the theoretical maximum efficiency, and it corresponds to the area of the solar spectrum that can be converted from one technology up to another. And one other answer it can be that you can have multi-junction solar cells from some specific applications, and you basically add different materials on top of one another. And with these different materials, you are able to absorb a bigger part of the solar spectrum. And currently, the maximum efficiency of these technologies are around 50%. But of course, they are extremely expensive, and they are basically only used for spatial applications. But if you take silicon technologies, very used worldwide, the common efficiency are about 20% today, and we have still 13 points of efficiency improvement. So it gives you a nice future development for PV technologies.
Yeah, thank you. Before I will invite you also later to respond on the issue of advanced technologies, because you are also in the research institution, I will respond to a few of the questions here. You have already talked about the charge controllers. What I will say is that these charge controllers, there's somebody who is asking, are these charge controllers and inverters same for rooftop PV and large-scale solar power plant? I'll say yes, and of course, the person who or the engineer who is working on this on your system will have to determine which is the best charge controller or inverter to be used. For instance, if it's a small system, yeah, for home lighting and basic use, then definitely for cost reflective issues, you will just go for a PWM charge controller, maybe. Or a shunt type charge controller, which is quite cheap and simple to get. Otherwise, for grid tied systems, of course, you have to go to a higher, and of course, depending on other factors from the utility, they might have specific conditions that you have to fulfill when you are agreeing on how to feed in your power. So the charge controller and inverters really varies on the site, because these are renewable energy systems, and the application is actually site specific. Then you have responded on efficiency. I will respond again on other aspects that affect the performance of a PV cell. Yes, somebody asked about soiling or dust cover. These are very important aspects that affect the performance. Shedding is also another very important thing, that when one of your PV module or a cell is covered, that does not receive quite similar irradiation with the rest, then you might have performance of that solar PV module drastically reduced, and therefore affecting the what you can be able to get. Then aging as well is also one of the things. And sometimes we have specific factors that really affect performance. During installation, the cracks might be on your solar modules, among many other physical damage. Sometimes even materials that have been used. Sometimes you find that the cover glass of a solar PV module keeps on aging differently. And becoming kind of milky, then this automatically affects the amount of photons that are reaching your cell, and therefore affects the performance of of your solar PV. So, just one more question before I pass it over. On the issue of battery life. Battery life is affected by quite a number of factors. One is the depth of discharge. Yeah. How much are you discharging? Yeah. The cycle, number of cycles that are being applied. Even the type and technology of the battery really varies and matters in terms of how long a battery should live. So I think with that, seeing the time is really not on our side, unless you will take on the question of the advancing trend before we can send it back to Fiona.
Yeah, I think we're good in answering the questions. Maybe one more parameters for the battery life is about temperature. Because you might know that increasing the temperature around your battery will also increase the capacity, but will decrease battery life. So temperature is also of key importance while you are thinking of how many years that can last a battery park. So sorry, we didn't manage to answer all the questions. We had so many. But we might answer these questions with maybe a written article right to the webinar recording. So now I think, Fiona, you can maybe I'll let you to conclude this webinar. I think you have your, yeah.
Thank you, Antoine, and thank you firstly to our participants for such fantastic and engaged questions. It's really wonderful to see your interest and to see how inspiring and thought-provoking today's webinar was. Thank you to Fred and to Antoine for a very informative and very interesting session. As I mentioned at the start, we will be putting a recording of this webinar online on the ISA Infopedia platform in the coming days. I encourage you to check out this fantastic resource. The address is on the slide on the screen, and to stay in touch with the ISA for details of our future webinars. For those French speakers or with Francophone colleagues, I note we will be running a French version of today's webinar on Tuesday, the 16th of June. You can register through Eventbrite, and I encourage you to share this with those who may be interested. So thank you once again to Fred and Antoine, and to the East African Centre for Renewable Energy and Energy Efficiency, and the French National Institute of Solar Energy for another fantastic webinar. We're very fortunate to be partnering with those institutions, and we very much hope that you can join us soon for the next webinar. In these challenging times, please stay safe, please stay healthy, and we look forward to you joining us soon. Thank you.